Having talked about the fundamental concepts of velocity, acceleration, displacement, etc., let's try to understand how we can use the three equations of motion in case of two dimensions. So the equations of motion are valid in 2D also if the acceleration is constant. The condition is exactly same as you learnt in 1D motion. Now acceleration constant essentially means the acceleration vector must be constant. It should not be a function of time. So it should be a constant I cap plus a constant j cap. If it's three-dimensional, it should be constant I plus constant j plus constant k. Only then equations of motion will be valid. So all the three equations of motion are written here in the vector form. You can have a good look at them. Now how to use them in 2D? There are two ways. The first way essentially is to use them directly in the vector form. So if you have been given displacement as ai plus bj, then you can directly use ai plus bj in place of s vector. And similarly, you can put similar vectors for u, a, etc. And then you can directly calculate the value of unknowns. Or what you can do is you can treat the i cap and j cap direction separately, which means you can apply equations of motion along x and along y separately as if you are applying those equations in 1D, in one-dimensional motion problems. And then once you have done that, you can later combine together the two results and get the final picture. So we'll try to solve a problem by both these methods to get a firm idea about how to tackle problems of equations of motion. The first method was the direct method in which we put every vector directly in their vector forms in the equation of motion. So for that, we have been given the value of u and a that you already saw in the problem. The value of displacement can simply be written as 84 I cap plus y j cap, where y is the displacement along the y-axis. Now why am I able to write this? Because the final position along the x axis is 84 units and the final position along y is something we have to calculate, which we assume it to be y units. So if I subtract final position from the initial position of origin, we will obtain the same value 84 and y as our displacement. Now once we have found these values, we can use the equation of motion s is equal to ut plus half at square, where we put everything in the vector form as it is, you can see. So on the LHS we get 84i plus yj, on the RHS we get 5ti plus half into 3i plus 2j t square. Now half into t square is a scalar number which can directly be multiplied to the individual components. So once we do that and we club together the I cap terms, we obtain this equation as our final resulting equation. Now we have one vector on the LHS, one vector on the RHS equal to each other. Now what is the condition of equality of two vectors? They should have the exact same magnitude and exact same directions, which means they should have exact same x component and exact same y component. So what I'm able to do after this equation is that I can compare the coefficients of I cap and the coefficients of j cap separately, which will give me two equations in time. So let's see how we do it. We compare the I cap coefficient and we obtain 84 is equal to 5t plus 3 by 2 t square. And when we compare the j cap coefficient, we get y is equal to t square. From the first equation, we have only a quadratic in time. We can obtain the value of t and we can put the value of t in the second equation. So having calculating that, you can get t as 6 seconds from the first equation, and putting that value in the second equation, you get y as 36 meters. So the final position or the final coordinate point along the y direction will be 36 units. I hope this is very, very clear to you. Now let's try and solve this problem using the second method of separating two dimensions and applying equations of motion separately on them. So with that method, if I choose the x direction first as my one dimension, a straight line, the initial velocity along x is 5 meters per second because 5 meter per second was the given initial velocity in the problem. Now acceleration along the x direction is 3 meters per second square because the given acceleration was 3i plus 2j. So along the x it will be plus 3. Displacement along the x direction is 84 meters because the final position was 84 along x and initial position was 0. So the displacement is simply plus 84. If I use these three and I calculate time first using the second equation of motion, it will come out to be 84 is equal to 3t plus half into 3 into t square. Everything along the x direction only. And the time that comes out to be is 6 seconds. So it takes the object 6 seconds along the x direction to move from 0 to 84 when this initial velocity and this acceleration is present along x. Now along the y direction, I can say that my initial velocity is 0 because there is no j cap component in the u vector. Similarly, acceleration is 2 meters per second square because we had 3i plus 2j. So we have 2 meters per second square along the y axis. and displacement along y-axis is y meters that we have to calculate. Now from the first direction of x, we calculated the time taken by the object to travel up to 84 meters along x. Now that much time only passes along y also. So we have been given the value of time this time and we have to calculate the value of y. So once again, if I apply s is equal to ut plus half at square along y direction, I'll put the value of t as 6 that I obtained from the x direction. So if I put the value of t as 6 and everything else as it is, here uy will be 0 because it is 0 meters per second along the y direction. I obtain y as 36 meters. So the final position along the y direction is 36 meters. This is the same result that we obtained when we use the direct method. So both the methods are equally correct and you can use either of them depending on the situation. So summarizing what we just learned, I can say that equations of motion are equally valid in 2 dimensions as they are in 1 dimension. The only constraint is that acceleration must be a constant. It should not be a function of time. And the motion of any particle in 2D can also be analyzed as motion of two simultaneous 1D. I am repeating this concept again and again because we will be using this readily in analyzing projectile motion. I hope it is clear to you. Thank you.